morning friends, welcome back. In our previous lecture we estimated what will be the thrust requirement or what should be the thrust available from the power plant or the power available from the power plant if it is a propeller driven aircraft at different velocities, right. That means what are we doing here? We are trying to perform engine sizing, right. So, if you look at a typical profile of mission profile of a UAV, what it has to do is it has to climb to a particular altitude and then say cruise or say loiter, which effectively is a cruise here, and then descend to the home, right. So, this loiter is performed by cruise, right. So, what we have estimated is what should be the minimum and maximum power requirement or the power requirement maximum for this particular profile, right. So, say for this particular cruise we are able to estimate what is the maximum power requirement, which depends upon the corresponding velocity for power required or say maximum. It depends upon the maximum velocity of flight, right. Say we have V max, the corresponding power requirement maximum. So, from here we are able to select one number from with which we can actually select the power plant, right. So, this will be one of the criteria for selecting this power plant. At the same time, we should also look at other phases of flight. Say here we have rate of climb or what we call it as climb phase. So, we should also look at the power requirement during this climb phase, so that the overlap of this, if you plot this power requirement for climb as well as the power requirement for cruise, so your power plant should be able to deliver the power that is required. It should satisfy both climb phase as well as the loiter phase, which means it has to deliver the power that is required during the climb phase as well as this loiter or cruise or say whatever during the surveillance phase of this, right. So, we should also understand the requirement of this climb phase. At the same time, we should know how this power requirement changes during this climb phase, what are the parameters on which this power requirement depends upon, so that you can correspondingly select the engine, right. So, finally, whatever the engine that you are going to select should satisfy the requirement of this climb as well as cruise phase. Now, let us look at what is this climb. So, for cruise we know L is equals to W and T is equals to drag, right, which we derived from general equations G1, G2. Now, let us go back to this G1, G2. So, when we move this UAV at a particular velocity, so we have lift acting perpendicular to it and drag acting along this V infinity, right. So, the weight of the system acts perpendicular to the local horizontal. So, this flight is moving at an angle gamma with respect to this local horizontal. Right. The corresponding component of weight perpendicular to this V infinity is W cos gamma, where this is gamma. The component of weight acting along V infinity is W sin gamma. And there is a thrust misalignment epsilon, right, with respect to free stream. Now, what we derived is equations of motion along and perpendicular to flight path, which is T cos epsilon minus D minus W sin gamma is equals to m dV by dt, right. So, this is our G1, and the other equation is L plus T sin epsilon minus W cos gamma is equals to m into V infinity square by r, where r is the corresponding radius of turn, right. This is the these are the equations of motion in the vertical plane, right. So this is your r1, this is. So say this aircraft is performing a loop in this vertical plane, right. Now let us look at a steady climb. So as the name indicates, it is steady where the acceleration is 0, right, and you have gamma since it's climbing, and further assume that epsilon is 0. This you might have already done during your performance course, right. So let us look at the corresponding power requirement with the help of these equations. Now this G1 and G2 reduces to the following with the help of these assumptions: T minus W sin gamma is equals to 0, and which implies W sin gamma is equals to T minus D. Okay. This implies sin gamma is equals to T minus D by W. Let us say this is climb, right, steady climb, SC1, or say CL1, climb 1, let this be CL1, equation be CL1. Now what about G2? Substitute this assumptions in G2. What we have here, L plus 0 minus W cos gamma is equals to 0. This implies L is equals to W cos gamma. This is climb CL2, climb 2. Equation for second equation for climb. This is the first equation for climb, right? So what do you observe from here? So this I can rewrite this equation, right? This equals to, so say T is equals to D plus W sin gamma, right? In case of cruise, we have T is equals to D and L is equals to W. So the lift requirement during climb is less than the lift requirement during cruise, right? Because this is for climb CL, CLI, right? What is CL for cruise? CLC is W. So if I divide these two, what I have is CLC into cos gamma. CL lift for climb is equals to lift for cruise into cos gamma, which means the lift for climb is less than the Since cos gamma, the limits are less than or equal to 1, right? Maximum value of this cos gamma is 1 here, right? So when this cos gamma will be 1, when gamma is 0, that means that's a maximum case for this particular equation is cruise, right? So see, lift for climb is less than that of cruise, but say with the same aircraft we want to cruise and we want to climb. That means the weight of this aircraft assumed to be, let us assume the weight of the aircraft is same. Since the lift is less in this case, but who is balancing the rest? Because the weight is same, we need to produce lift equal to weight in order to have this flight. So the thrust is taking the additional load here, right? So in case of cruise, we simply have T is equals to D, but in case of climb, we have another component W sin gamma. Right? This is an additional component. So when this additional component will be 0, when gamma is equals to 0, right? When sin gamma will be 0, when gamma is 0, that means if you consider a gamma 0 flight, which is a level flight. So we already have a steady condition here, it becomes a steady level flight. Climb will become a steady level flight in this case. So that means, so you need to produce more thrust compared to that of a level flight here while climbing. So this additional weight is taken by the engine, right? So the engine will lift the additional weight here in this case, or the power plant. So CL3, climb 3. So what does it mean here? Sin gamma is equal to T minus D by W. So say for a steady climb with these assumptions, we have thrust and we have V infinity. What we have is drag and we have W sin gamma. We have lift and we have W cos gamma. Right? This particular angle is the climb corresponding angle of climb, right? Gamma. So this is a FBD for this particular case. So this gamma is the climb angle given by T minus D by W, right? So what are the factors that affect this gamma? Say, if I want to reach a particular altitude, say H2 from an altitude H1, so how fast I will reach this altitude, right, is known as rate of climb. So say I want to reach within a time delta T, right? So how fast I reach from altitude H1 to H2 is given by dH by dt, which is the H dot here is a H2 minus H1 divided by delta T. See, what is H2 minus H1 by delta T? It's a component of velocity in this vertical plane along the vertical axis, right? So this component of velocity along this vertical axis is known as rate of climb, R by C. Right? Now we have V infinity here along, see we have V infinity of this aircraft, right, inclined at an angle gamma. What will be the component of this velocity in the perpendicular direction, perpendicular to local horizontal? Or what is V component of V infinity along the vertical axis? This is V infinity sin gamma right? Am I correct or not? See what we have, we defined rate of climb, which is the vertical velocity, right? Which is h2 minus h1 by delta t, right? So this V infinity has a component along this vertical direction. Do you accept this? Since we are climbing at an angle gamma, the component along this vertical axis is V infinity sine gamma. This is equals to V infinity sine gamma. Right? So what is sine gamma? Rate of climb is equals to V infinity sine gamma is equals to V infinity into T minus D. So this is from equation climb 1, right, CL1. Right. So CL1 says sine gamma is T minus D by W. So simply substitute the T minus D by W here. This implies T into V infinity minus D into V infinity by W. So if you see, there is a climb. Whenever there is a climb, there is a corresponding angle, climb angle. So this is possible only when you have some additional force. Don't you see this? See what is T? T is the thrust supplied, right, from the engine. It is the output from the engine, and D is a requirement of the system. So D is a requirement of this system, of this UAV. Drag is the required force, like the drag should be, I mean an equivalent opposite force need to be supplied to the system for a level flight condition. But in case of this, you have, for a climbing flight, you need to produce a bit more force, right? So drag is the requirement of the system here. So T is the output from the power plant, D is the requirement, right? That means this difference is the excess thrust. If say D is the requirement and T is the available thing, so the difference of this is the excess thrust that is available. So this is known as T minus D by W is known as specific excess thrust. So gamma, climb angle, depends upon this specific excess thrust, right? This similarly here, T into V infinity is the power available from the system, right? D into V infinity is the power required by the system. This we already discussed in our previous lecture, where rate of climb is equals to power available minus power required by W, right? So this is the specific excess power. The difference between this available power and required power is known as excess power, or divided by W is known as specific excess power, right? So this depends upon, rate of climb depends upon excess power. Higher the specific excess power, greater is your rate of climb, right? So rate of climb is equals to power available minus power required by W, right? So this I can express as so one more term to introduce is this, the ratio of power to weight is known as, right? Now the rate of climb depends upon the specific excess power. So for the maximum rate of climb, I need the minimum power required. Can we prove that? So what is rate of climb there? Rate of climb is equals to T by W minus, or say 1 by W times T into V infinity minus D into V infinity. This equals to 1 by W T into V infinity is the power available minus half rho V cube S into CD naught plus K CL square. Right. So rate of climb is equals to 1 by W into power available minus half rho V infinity cube S into CD naught minus half rho V infinity cube S into K into CL square, right? This is CL square. From the second equation of climb, we have L is equals to W cos gamma right. So for small angle of climb, this can be closely assumed as L is equals to W. So the corresponding CL is 2 W by S by rho V infinity square, right. Substituting this in the above equation, what we have is rate of climb is equals to, so what is this number? This is CL 3, right? What was this equation? So this you consider it as CL 4. Yeah, consider this equation as CL 4. Rate of climb is equals to. Okay, say this as CL 4 and this as CL 5. Okay, consider this as CL 4 and the last equation as CL 5. Now we have rate of climb is equals to 1 by W times power available minus half rho V infinity cube S into CD naught minus half rho V infinity cube S into CL square will be 4 W square divided by rho square S square so V infinity cube V infinity to the power of 4. Sorry, right. So rate of climb is equals to 1 by W power available minus rate of climb. If I need the maximum rate of climb, for this rate of climb max, I differentiate this rate of climb with V infinity and equate it to 0 for rate of climb maximum, right. So that implies minus 3 by 2 rho V infinity square S into CD naught. This will be minus plus 2 W square into K by rho into S into V infinity square. This equals to 0. Right. This implies V infinity to the power of 4 is equals to 4 by 3 W square into K divided by rho square s square rho square s square by 3 by 3 CD naught. This equals V infinity is square root over 2 W by S by rho, right, 2 square 1 by 4 root over 2 W by S by rho into K by 3 CD naught raised to the power of 1 by 4. So, this is the velocity condition for the corresponding rate of climb maximum. This is the corresponding velocity condition. So, do you remember this equation? So, what is in general velocity? Velocity during the flight, either climb or cruise. Let us say in cruise, let us say. What is the corresponding velocity of flight? Will be twice the wing loading under root, twice the wing loading by rho into corresponding CL, CL of flight. So, here can you see this CL is square root over 3 CD naught by K, right. The corresponding CL for this particular case is CL is equal to square root over 3 CD naught by K, and this velocity is the minimum power requirement velocity. So, that is the reason why we mentioned power required is minimum, right. So, if you fly at minimum power requirement, this particular quantity is less, we have higher specific excess power from a given power plant. That means, if you are operating at the maximum power, you will have the corresponding maximum rate of climb. So, this condition corresponds to CL power 3 by 2 by CD maximum, right. When you do CL power 3 by 2 by CD max, the corresponding CL value is root over 3 CD naught by K, which is the minimum power requirement condition in a level flight. So, why both are same, rate of climb maximum and minimum power requirement. So, while differentiating this equation, this rate of climb with V infinity, what we assumed is this power available is constant with velocity, right, which means is not affected with velocity, but indeed it is not true unless you use a variable pitch propeller for different altitudes, and it will not exactly remain constant, right. So, that is one assumption that we have considered here, and this power available is shaft power times the efficiency, right, and moreover this efficiency factor is also assumed to be constant with velocity here. Right. So, say you know what is the corresponding velocity for rate of climb maximum, right. Now, let us say, how do you select a power plant based upon this? We have two parameters right now. For in case of a small UAVs, we have cruise and the climb are the major phases of this flight, right. And you got to know what is the power requirement in cruise, maximum power requirement. At the same time, we should also get to know what will be the power requirement or what should be the power supplied to the system from the power plant for various climb rates, right. So, if we can rearrange this equation, if you understand that power requirement, then you can select, okay, what you pick up the maximum thing, maximum power requirement of the total flight envelope, and then correspondingly with an efficiency factor select the power plant, right. What you need to take as an input is this rate of climb, right, for different rate of climbs. So, we have rate of climb into W is equals to power available minus power required, right. So, for different rate of climbs, right. So, consider rate of climb as an input. So if I want to say, if I want to get a plot where this power available and thrust loading and the rate of climb, for different rate of climb, what should be the corresponding power available to weight ratio? What is the maximum rate of climb that your UAV has to do, right? It has to perform. So the corresponding power requirement you will select. And based upon that power requirement, you can select the corresponding engine, right? So how to calculate that? How to get that, right? So consider steps. Consider the rate of climb, desired rate of climb, and plug in that rate of climb into this equation, which is CL 5 and 6. It is, say, CL 6 or no. So this is your CL 6. This is your CL 7. And this is your CL 8. Right. So the aim is to figure out what is the corresponding power required for different rate of climbs, or say what should be the output from this power plant for the different rate of climbs, right? So you know, from the mission requirements, you can fix this particular rate of climb, what should be the maximum rate of climb that your aircraft has to perform. So for that maximum rate of climb, you can figure out what should be the corresponding power available from the system, right? Because the V infinity for this maximum rate of climb, you can arrive from this equation, right? And say if you want to plot the variation of power available, the power loading with rate of climb, what you need to do is plug in the values of rate of climb and find out what is the power required by W, correspondingly plot the values and figure out. So for the specific power for the specific rate of climb, what is the corresponding power available from the system, right? With that number, you can select your power plant. You can consider that number while selecting your power plant, right? Now let us consider an example. Select a power plant, a propeller driven, power plant for a fixed wing crop delta UAV. Weighs 3.5 kg and 0.787 meter square wing area. During steady climb. Steady climb. During a steady climb, velocity of this climb is 20 meters per second. During a steady climb to reach an altitude (1 kilometer) in 3 minutes. Assume K is 0.16. So what we need to do, we have to select a power plant for this configuration, which has to perform a steady climb, and the climb altitude should be 100 meters from sea level, 1000 meters from sea level, and it has to reach this altitude within 3 minutes. Let us look at the solution. So if you have to select a power plant for this particular mission profile or particular phase of this mission, we need to understand what should be the power required by this system, right? Total power required by the system during the climb, right? So that power should be delivered by the power plant. What is given? So this is your desired altitude h, which you need to attain. So this desired altitude need to be attained within delta t of 3 minutes. So this you consider delta t at t is equals to 0 and t is equals to 3 minutes. Right. So from our equations, and we know V infinity is equals to 20 meters per second velocity during this climb. So we know rate of climb is equals to power available minus power required by weight of this configuration, right? So I need to know what should be the power available from the power plant to perform this particular task, so that I can select the corresponding power plant. W into rate of climb, right? So this power available is equals to rate of climb into W plus power required, which is drag into velocity, right? This is the power required in this case. So this is drag into velocity. So power available is equals to rate of climb into W plus half rho V infinity cube S into CD. This equals to, so if we know what is CD here, we know what is velocity of climb, we should know what is the rate of climb in order to find out what is the corresponding power output from the power plant. Okay. So what is rate of climb is dH by dt, which in this case is dH is 1 kilometer, 1000 meters. It is given here, right? We need to climb 1000 meters in 3 minutes. So what we have is 1000 divided by delta t is 3 into 60. This is meters per second, which is approximately 5.55 meters per second. So from here, can we estimate what is the climb angle? Since we know rate of climb is V infinity sine gamma is equals to rate of climb, right? So this equals to 5.55 meters per second. This implies V infinity, sine gamma is equals to or gamma is equals to sine inverse rate of climb divided by V infinity, which is sine inverse 5.5 divided by 20 meters per second, because the velocity during the steady climb is 20 meters per second, right? So this is approximately 16 degrees. So the corresponding angle of climb is 16 degree. Now we know what is rate of climb, what is the corresponding angle of climb. We need to calculate what is the power requirement during this condition. So that is drag into velocity, right? So what is CD? How do you get CD? CD is equals to CD naught plus K into CL square, right? So we need to know what is the corresponding CL for this flight condition, right? So we have another equation from climb to, we have L is equals to W cos gamma, right? So this implies CL is equals to twice the wing loading divided by density into V infinity square into cos of gamma. This implies this is 2 into W by S is W is 3.5 into 9.81 divided by 0.787. So wing loading into cos of 16 degrees divided by 1.225. It's an assumption that we are taking. So now this density 1.225 is an assumption here that we are considered. Else you can also take an average value, which is the mean of density at 1 kilometer and sea level density, right? So into V infinity square. What is V infinity square here? It's 20 meters per second, 20 square. So what is CL value here? CL is equals to 0.171, right? If I am not wrong, 0.171, right? And yeah, 0.17. Now you got the value of CL. You know what is K. You substitute the value of CL and K in this equation, right? So CD naught should be given, right, in this question. So let us take CD naught is equals to 0.035, right? So you can refer to your previous example that we have solved. It's the same configuration. What is CD? CD is equals to 0.035 plus 0.16 into CL square is 0.171 square. This sums up to be CD is equals to 0.035 plus 0.0047 is a 0.397. CD. So now you have CD, you can substitute in that equation. So what we have, power available is equals to rate of climb into weight of this aircraft plus power required, which is drag into velocity, right? So this is rate of climb into W plus half rho V cube S into CD. So what is rate of climb here? 5.5 meters per second. That's a vertical velocity into 3.5 into 9.81 plus 0.5 into 1.225 into 20 cube into 0.787. What is the CD value? Is 0.0397. So the power available should be 341.54 watts. So, this should be the power output from the power plant, right. You should select a power plant which can deliver this much of power, useful power, right. Now, but we know power available is propeller efficiency into shaft power, right. So, each engine is specified in terms of, or the specifications of the engine are presented in terms of shaft power, available shaft. So, this P shaft power is equals to power available by efficiency of the propeller, which is 341.54. So, assuming a propulsive efficiency of 0.85, consider eta P as 0.85, okay, 0.85. What you get for this shaft power is 415, so 401.81, yes, 401.81 watts. So, what do you think is the distance, horizontal distance covered during this climb, right? You can also estimate that horizontal distance here. So, the horizontal distance travelled, let us say x is equals to, since we are climbing with a constant velocity, right, v infinity into or component, horizontal component of velocity into delta t, since velocity is constant, right. So, what is the horizontal component of velocity? So, climb velocity into cos component of this climb velocity, right, cos gamma into delta t. This equals to 20 meters per second into cos of 16 degrees into delta t is 3 into 63 minutes, right. So, this is 20 times 0.96 approximately into 190. This is approximately 3.4 kilometers. .460. So, this is approximately 3.461 kilometers. Okay. This is the horizontal distance travelled during this climb.